Various components of electronic circuits communicate and work together through signals that consist of variations of current or voltage. A signal can be made of continuous variations of current or voltage, as in an analog signal. Or, a signal can be made of discrete values of current or voltage, as in a digital signal. A digital signal can only have a low and a high value of current or voltage represented by the numbers 0 and 1 respectively. Thus, digital signals consist of strings of zeros and ones called binary numbers. The circuits that control the flow of digital signals on the basis of a logical relationship between the input and output signals are called logic gates. The 5 commonly used logic gates are the AND, OR, NOT, NAND, and the NOR gates. Let us use simple circuits of one or more switches and a bulb to understand logic gates. Here, the state of the switch is the input that determines the state of the bulb that represents the output. An open switch represents an input of 0. The bulb remains off in this condition and represents an output of 0. A closed switch represents an input of 1. The bulb lights up in this condition and represents an output of 1. Now here is a circuit representing an AND gate. An AND gate has 2 or more inputs. The 2 switches A and B represent 2 inputs and the bulb O represents the output of the logic gate. Let us list all the possible input and output combinations of an AND gate in a table. When both the switches A and B are open, no current flows from them, so both the inputs are 0. The bulb in this case remains off, hence the output is also 0. When switch A is closed and switch B is open, input A is 1, while input B is 0. The bulb in this case still remains off, hence the output is still 0. When switch A is open and switch B is closed, input A is 0, while input B is 1. The bulb in this case again remains off, hence the output is again 0. When both the switches A and B are closed, both the inputs A and B are 1. The bulb in this case turns on, indicating this time that output is 1. An AND gate is represented by the symbol shown here. The table that lists all the logical input and output combinations of a logic gate is called the truth table of the logic gate. Thus, the table shown here is the truth table of the AND gate. The output of an AND gate is 1 only when inputs A and B are both 1. Now let us learn about the OR gate. Here is a circuit representing an OR gate. Just like an AND gate, an OR gate also has 2 or more inputs. Let us form the truth table of the OR gate. When both the switches A and B are open, no current flows from them, so both the inputs are 0. The bulb in this case remains off. Hence, the output is also 0. When switch A is closed and switch B is open, input A is 1, while input B is 0. The bulb in this case turns on. Hence, the output is 1. When switch A is open and switch B is closed, input A is 0, while input B is 1. The bulb in this case again turns on. Hence, the output is again 1. When both switches A and B are closed, both the inputs A and B are 1. The bulb in this case yet again turns on. Hence, the output is again 1. The symbol and the truth table of an OR gate are shown here. The output of the OR gate is 1 when either input A or input B or both are 1. Now, here is a circuit representing a NOT gate. Unlike the AND and OR gates, a NOT gate has only one input represented by switch A. Let us form the truth table of the NOT gate. When switch A is open, no current flows from it, so the input is 0. However, the bulb is turned on, hence the output is 1. When switch A is closed, assuming 0 resistance in the switch, all current flows through the switch and no current flows through the bulb. Thus, input is 1 and output is 0. The symbol and the truth table of a NOT gate are shown here. From the truth table, we can see that a NOT gate inverts the input. Thus, it is also called an inverter gate. An AND gate followed by a NOT gate forms a NAND gate. The symbol of a NAND gate is a combination of symbols of the AND and NOT gates as shown here. Note that in a NAND gate, the output of the AND gate acts as the input for the NOT gate. The output of the AND gate is inverted by the NOT gate and appears as the output of the NAND gate. Hence, if inputs A and B are both 1, the output of NAND gate is not 1. An OR gate followed by a NOT gate forms a NOR gate. The symbol for a NOR gate is a combination of symbols of the OR and NOT gates as shown here. In a NOR gate, the output of the OR gate acts as the input for the NOT gate and thus gets inverted. Thus, the input values in the truth table of a NOR gate are taken from the input values from the OR gate table. The output of the OR gate is inverted by the NOT gate and appears as the output of the NOR gate. NAND and NOR gates are also called universal gates, as they can be used to create all other forms of logic gates like the AND, OR, and NOT gates. Logic gates in a circuit are realized by combinations of electronic devices like diodes and transistors in combinations with resistors, inductors, and capacitors. For example, here is a circuit showing the construction of a NOT gate. Conventional circuits using a large number of electronic devices assembled together are bulky, unreliable, and prone to malfunction. Such circuits that use individual components are called discrete circuits. In 1958, Jack Kilke of Texas Instruments in USA created an integrated chip or IC that allowed circuits of a large number of electronic devices to be created on a single small chip of a semiconductor. The invention of ICs revolutionized the development of digital electronics, allowing increasingly complex circuits to be built onto increasingly smaller single semiconductor chips. Depending on the nature of the signal it can process, an IC can be an analog IC or a digital IC. A digital IC contains the logic gates we discussed before. Depending on the number of circuit components built on it, an IC can be classified as a small-scale integration IC, medium-scale integration IC, large-scale integration IC, or a very large-scale integration IC.